Fixing computers is hard enough, but fixing computers that other people tried to fix and failed, that's just asking for punishment. This is another one of those computers that someone tried to fix before, and they didn't succeed and probably made things a lot worse. Fixing other people's bad repairs is actually kind of one of my nightmares, but last time I did a video about it, you all told me that you really enjoyed that and you wanted to see the other Amstrad repaired, so today is the day. So one of the most common ways that I start with this is by just looking at the power draw of a computer when I know nothing about it other than it's not working. So I plugged in the bench power supply, and now when I turn on the power here and the switch in here, we'll see how much current is going to draw. And 0.6, 0.7, that seems probably okay. It seems a little low, but it may depend even on the kind of gate array that this computer has. All right, let's have a look inside. So right away, this is the 40,010 gate array, and that one consumes less current than the older one, than the 40,007. So maybe then the 600 milliamps is okay. Right away, I'm seeing some things. Well, obviously, there's an EEPROM in here, but my friend already told me he was messing in here. So the CPU is socketed, but I think that's normal. This is definitely normal. And I'm also seeing some capacitors that don't look original. I think the original ones are these flat ones that are usually all over. I'm surprised those were replaced. Oh, right, the RAM has all been socketed as well. So we could have some missing traces, like in the previous CPC repair video. Let's see the back. Oh, okay. Yeah, that doesn't look good. I definitely see traces that were pulled and they were kind of patched, some wires there. The RAM looks cleaner. So yeah, you can tell the capacitors were replaced. That's all new solder in there. Oh, has this one been replaced as well? I think so. Yep. Wow, so many things socketed. Who knows what might be wrong here? Where to start? Hey, I want to take a second to thank today's sponsor, PCBWay. PCBWay offers PCB manufacturing, which is a great service for all your prototypes and projects. You can go directly to their webpage, upload a Gerber file, change a few parameters, and get an instant quote, and you can start the process right away. They have a really quick turnaround time, so you may have the boards back in your hands in just a matter of a few days. This kind of service is great for the final stages of a project when you can iterate quickly on the board, fixing small mistakes until you have your final version. If you're interested, go ahead and check out their webpage at PCBWay.com, and thank you, PCBWay. Okay, here's what I'm gonna do. I'm going to test voltages, even though we've already seen that it's probably fine given the voltage at the bench power supply. It's a step that takes nothing and it will save us potentially a lot of headache. So I'm going to use this connector that I've made before that just hot wires the switch, so I don't have to connect the whole top of the computer. So whenever we power on the bench power supply, the board will be powered. And I will just randomly measure the voltage, maybe at the ROM. Ooh, 4.1. That's on the low side. The Amstrad always tends to have lower voltage than usual. It's definitely not a rock solid 5 for some reason. Well, it doesn't have a voltage regulator, but even though you feed it 5 from the power supply, it drops down some, 4.7, 4.8, but 4.1 seems really low. I wonder if anything is warmer than the ordinary. This is actually a perfect time to use this thermal camera that was sent to me by TopDon, and I've only used it a little bit so far and I've been really impressed with it, but I haven't used it in a deep repair, so it hasn't shown up in a video yet. So this will be my first time using it in a video. So this just connects to the phone like that. The Z80 gets warm. The gate array, notice, it's pretty cold. And that's because this is the newer one that is more efficient, like we were talking about before. If this was the older one, it would be glowing hot. It even has a heat sink. So I'm not used to having a thermal camera, so I don't know if the Z80 at 50 degrees is normal or not. I mean, that seems hot, right? But I mean, it is hot to the touch. And that one, RAM IC, is definitely a lot hotter than that other one. I'm gonna try removing the ROM and even maybe the RAM ICs and see if the voltage drop becomes more reasonable. Both the ROM and the RAM are not really necessary for the diagnostics. 4.4. Just a little higher, but still pretty low. Wow, I just noticed these sockets. Check this out. This is horrible. What happened here? Like, somebody melted the socket, and yeah, I mean, this IC, whoa, some of these are even missing. They're missing the metal connector there. So this RAM IC was definitely not making any contact. And this one probably wasn't. And this one looks way too open. Wow. I don't have my hopes up at all, but maybe the next thing I'll do is I'll run the diagnostics ROM without the ROM or the RAM. In order to do that, I need to clean this expansion port. It just looks way too dirty for that, so I'll use one of these. My favorite tool for this is a fiberglass pen. Now I'll just clean it with some isopropyl alcohol. Yeah, that looks much better compared to that one. Big difference. So it looks like the board is mostly dead. We should have gotten something on the screen if the Z80, the gate array, and the CRTC were functional, and the buses, I guess. But we're getting absolutely nothing, so something is very dead here. So my suspicion is that the Z80 is not working properly, and the correct way to test that would be to take the Z80 and put it on a working computer and then see what happens. But instead of doing that, which would be the logical thing, I want to learn a little bit more about temperature ranges and normal ranges. So what I'm going to do instead is I'm going to open up this Amstrad computer, which is going to be very similar on the inside to the one that we're repairing, and I'm going to leave it running for a few minutes and see what the temperature the Z80 gets to. And that will be very useful in future repairs. So at a glance, I can see, oh yeah, that one is overheating or not, now that I have the thermal camera as a tool. So this has been running for a few minutes, and the CPU is, yeah, it's up there with almost 50. Yep, it is 50 degrees. So that was not a problem. I guess that is a normal running temperature for the Z80, at least on an Amstrad CPC. I'm seeing a couple of interesting things on this particular board though. First of all, it surprises me that the PAL over here is so much hotter. I mean, I guess not super hot, but it looks very bright. It surprises me that for such a simple chip that it's using up so much power. The other really cool bit is that this is a 6128 board. So it has those two rows of RAM ICs. One of them is the lower 64K and the other one is the upper 64K. The upper 64K is not being used when you just turn the computer on, and it's all in the lower 64K. That's where the screen resides. That's where some of the basic variable and working space is. And you can tell the difference. You can see that this one row here is hotter than this one. So this is definitely the lower 64K, and I know that, but it's very cool that you see it visually like this. So let's first swap out the Z80. Nice that it's socketed. Oh, we get nothing. So it looks like the Z80 was definitely bad, at least. Let's see how many things were bad in the other one. So I just swapped the gate array, and oh wow, nothing still. I'm starting to think that that whole board was fried. That's going to be a lot of work. I didn't really have my hopes up, but just in case, I put in the Z80 and the working gate array on this board, tried the diagnostics ROM, and nothing, kind of like I expected. So I think at this point, we should just have a look at it in the oscilloscope and try to see what's working and what's not. The first thing I'm gonna check is to make sure that the reset line of the Z80 is not set to low all the time because it's active low. I've been bitten by that a few times, and that seems fine. Okay. So some of the activity that I check to make sure that the Z80 is alive, I check for the I/O request and the read and write signals. So yeah, read, write. They do look kind of ugly though, don't they? But sometimes those signals are kind of ugly. The other really important one is M1 and refresh. So this is refresh, okay, and M1, okay. So the Z80 is trying to do things. Let's check the data bus. Oh, that, however, is not good. This is 10, so yeah, this is data line 6, and that is not, I mean, I expect something like this. Not like that. So there's something there in the data bus that is fighting over things, which then explains why we're not seeing anything at all. So I'm looking at the schematic trying to narrow down what the problem could be with the data bus. And I guess we should just look at all the places that are touching the data bus. So obviously the Z80 itself is touching the data bus. The PPI is, yep, right there. The ROM is, we have removed it already, but that's fine. Interestingly, the RAM chips, which are not there, but the RAM chips only touch the data bus in the input bit. So this is the data bus. The output bit goes to a sort of private data bus between the get array and then some buffers and latches. And so those are in touch with the data bus. And then in addition to that, we have the CRTC is touching the data bus. Of all these things, most of them are, the data bus is an input. It's an input into the PPI, although maybe it's an output as well. Yeah, it has to be an output because the Z80 needs to read things back. So it has to be both an input and output. The one I was thinking is that of these two here, so these are the buffer and the latch. The buffer is for getting data into the memory from the data bus, probably so the data bus can change to something else, and this holds the data for the RAM. But the latch is the opposite. It gets the value from the RAM and then it holds it and keeps it in the data bus. So if something is wrong with this one, I would say it's more likely to interfere with the data bus than input only pins like here. So maybe we should start having a look at this one. So the output values in the latch should be what we saw earlier in the data bus. So some of them should be fine, yep, like that. And yeah, some of them are like that. And output enable. Oh, output enable is floating. And output enable is active low. So this is supposedly coming from an OR gate from IC11200, which is this one. It looks really ugly. It's been socketed and it's kind of sideways. So, And so just to make really sure, from 8 to 1, yep, we're not getting anything in there. Well, I guess we can start by fixing that. So right away, this socket is not as bad as this other socket down there, but I'm seeing some things I'm not liking. There's some chipping in there of the pane. That's probably fine. There's a very thick trace. There's probably ground or a VCC, but chances are somebody tried to push the chip that was there and force it, and that's why they got that. So I'm not too surprised if they lifted some traces. And even here, there's some scratching. Oh, I see what's happening. So this is what we want. This trace comes to this via here, and that connects on the other side to 8. It could even be what we saw earlier. Maybe it's that. Maybe that's enough to break the trace. Okay, so we do have continuity from here to here. It's just from here to here that is missing. So I'll do the usual and connect a bridge in there to get continuity back. And I'm not sure if that's going to fix our data bus, but that's certainly a fix that we have to do anyway. Let's see if that made any difference. No, no difference whatsoever. Except that now this should be on sometimes. Oh, it's never on. Right. Because it's high all the time and because the system is kind of locked and it's not trying to read back from memory, I guess. One thing about those lines in the data bus looking kind of weird could just be that they aren't really enough things hooked up to the data bus, and we're seeing times where nothing is being output. I've actually had that happen before. I've had nothing connected to the data bus and things look really weird, but it's really other parts, other signals of the board kind of interfering there a little bit and giving you fake signals that way. So I wouldn't put too much weight on what we're seeing and just keep focusing on trying to get the board to work. And now with that line fixed, we can finally run the diagnostics test. There's one thing that is really weird though. The test started correctly. We got that border color and some time passed while it was doing the memory test. But then it was supposed to tell us whether it passed or it failed. If it passed, it should have just filled the screen with some menus and some information. And if it failed, it doesn't even use the RAM. It just uses some tricks with a CRT controller to show you which ICs are failing. But we got neither one of those things. So that's really weird. So that makes me wonder, is it reading the ROM correctly? But I think it would, because the beginning really looks like it. One thing I added to the test is some beeping. Some beeping at the beginning to know that the test is about to start, and then some beeping at the end to let you know if it passed or failed. And we're not getting either one of those because I don't have a speaker hooked up in here. So I think what I'm going to do is I'm going to run that again, but hook up the top of the case, which is just a little uncomfortable, but that has the speaker connected. And that way we'll be able to hear what is happening. Is the test failing? Is the test never even getting to the end? That should help quite a bit narrow things down. Okay, let's listen carefully to see if we hear any beeps at the start and the end of the test. Wow, okay. So I mean, I hear some static, that's normal, that's just the volume wheel being dirty. It clearly started and ended the test because we heard the initial beep and then we heard some low tone beeps at the end, which mean the test failed, which obviously failed because there's no RAM in it. But we're not getting any of the display that we're supposed to get. We're getting this weird pattern actually. So those results are kind of puzzling. I don't want to jump to conclusions and say it's the CRTC for sure, because the CRTC was configured correctly at the beginning because we got that square box and everything. If we weren't able to talk to the CRTC and set the right parameters, we would not be seeing that screen configuration. But then it failed completely to set the correct configuration once the tests failed. So I don't know what to think. I don't want to pull it out because it's mostly working. So maybe what I'm going to focus on next is I'm going to try to repair the RAM area, since we need to do that anyway and it's a mess, and see if we can manage to get the RAM test to pass. And then see what happens. Do we get normal characters? Do we get a normal screen? Or do we get still weird things? So what I'm going to do is I'm going to start just by removing those two sockets. Those are just too far gone. And then I will check that we have the right signals everywhere and see if we have any other broken traces. Okay, with those two sockets out of the way and things looking a little bit better, now I'm going to check continuity on all the RAM pins. The way I'm going to do it is I'm going to do two things. First of all, most of the RAM chips have the same signals connected to all of them. As a matter of fact, all of them are the same except for data in and data out. All the address lines are the same, CAS and RAS are the same, VCC, all of that is all the same. Another thing is important to check that too is like those lines are, as you can see here, they're connected in series. So if somehow I pull the trace in here, then usually those two would also lose the same signal that is coming from, or actually probably the other way around. It's coming from here. It would probably, if I pull a trace there, then this chip would also not get it. So I need to check that they all have those signals in common. And then I need to check that the signals go to the correct place. For example, I'll check the data bits to the Z80 and CAS and RAS and things like that, that they go to their source. Okay, first one right here. This one is not connected. That is 1, 2, 3, 4. Okay, so surprisingly, only a few signals were not connected, which is just 4, which is RAS here and here, surprisingly, because I don't think this is connected. I can kind of see it right here. I think that's exactly where it's missing. And I don't know exactly why those are not connected. Maybe there's a trace from here to here. So I'll fix those and then populate this with RAM ICs that I know are working. Okay, that's fixed. I put two sockets because it was easier to make a bridge like that with sockets in there. And then it turns out that I only needed to do one connection because apparently the RAS signal comes down this way and then it turns around and it comes back this way. So obviously if this one was missing, like I said, these were connected in series and none of them had it. So now we have continuity everywhere. We have all the signals are good. I checked them against the Z80 and they're all fine. So let's see if we can make that test pass now. Oh, interesting. So this means the RAM tests passed, which is good. That we figured that. But notice when it stops printing. There should have been a whole screen here with more information and a menu and all that. And it is stopped as soon as it queried the CRTC for what type of CRTC it was. So I guess our earlier suspicion was correct. This CRTC is kind of working enough to set up the basic parameters for the Amstrad. But as soon as you try to do anything different, like in this case, query which kind of CRTC it is, or set weird border parameters, which is what it does when the RAM tests fail, it just, I don't know, I mean, it must return some garbage numbers, and that's why it throws off the ROM test. So let's take advantage that we have full access to the source code of the diagnostics ROM since I wrote that one. And let's see what exactly is happening that is causing the Amstrad apparently to hang. I was assuming that it was going in some weird loop, but let's see what happens. As I suspected, we print the string of CRTC colon, and then we go and get the CRTC type. So it's not like it was cached before and we were trying to print it there and then it would somehow pause. That makes no sense. We try to get the exact type at the moment that we print it, and that's when we're hanging. So it has to be in this function that there's something going on. Right, so here it looks like we are selecting a register. Oh, this is what's happening. If the CRTC was reporting some weird value, we would handle it and it would come up with CRTC value 0, 1, or 2. So there's drop-throughs for every option. But before we do that, we wait for a vertical sync signal. And this is just a loop that we keep doing over and over and over and over until we get the bit that says, yes, the vertical sync signal just happened. I'm going to guess that we're never getting out of this loop. We're loading F5 in the B register here and then doing an N. And then we get the value that we get back and we check to see if the bit indicating the vertical sync signal has happened. This F5 means that we're talking to the PPI, not to the gate array that knows about vsync, not to the CRTC that generates the vsync, but the PPI. I really had forgotten that that bit comes from there. So the PPI is here, and yeah, this is why it's surprising because it's the CRTC that generates vsync and is passed to the gate array. But somewhere at the PPI or PIO, it has different names for it, right? So right here, it receives vsync. Oh, right. So the PPI has 3 ports, has A, B, and C. Each of them has a different number and when you want to read or write to it. And F5 corresponds to the B port. So specifically, it looks like it's maybe, right, B0. So it's the lowest bit in the B port. And that's exactly what we were trying to do with the assembly. So the first thing I'm going to check is the vsync is connected correctly. Vsync at the CRTC is generated in pin 40. That's nice and easy. And it reaches the PPI at pin 18. Okay, well, that's fine. So I'm going to check the connection to the data bus of the CRTC because we've checked that already. So the data bus is fine. What else could it be? There's those address lines. If the PPI is not getting the right address lines, then it won't know that we're talking to it. It's also getting some control signals, IO read, IO write. Those are important. Those are generated from the read and write of the Z80. Oh, specifically, those are generated with an OR gate, and that OR gate is IC 112 which is this bad boy over here that was socketed before. And this is the one even had a trace earlier, right? We had to fix a trace from here to here. So it's very likely that something there is not connected correctly. So the IO request is generated from the IO write request from 22, yep, and 20, which is IO request in the Z80, yep, that's fine. And the output 3 goes to pin 38 here. Oh, no, 36. Yep, okay, that one is fine. IO read is from IO request, okay. And the read signal, which is 21. Oh, 21, I think we're missing that. And the output of IO read goes to pin 5. Yep, so I think we're missing this one. And that probably happened when they added the socket for that. Okay, once more into the breach. All right, let's do this. I've got a good feeling about this one this time. Yes, we got it. Wow, wow. I'm so glad to see this screen. Okay, I think all we have left is to figure out the ROM. Everything else, I'm pretty confident it seems good. It's just that I haven't even attempted to put a ROM in here because this looks so horrible. I looked at all the traces in the ROM and they were miraculously all connected correctly. So I went to power it on, and right before I did, I had a better look at the EEPROM that was installed in there. And guess what? This is a 27C128, which means it's a 16 kilobyte EEPROM, which means there's no way you're booting up the Amstrad into the basic prompt because it needs two 16K ROMs. It needs the OS in the lower 16 kilobytes and the basic interpreter in the upper ROM 16 kilobytes. So I have no idea what's in here, but this is not gonna work. Fortunately, I had another ROM lying around. This is not the exact correct one. This is the English one for a 464, but this one will let us get into basic. All right, let's try it. I'm really hoping this works now. Wow, still nothing. All right, so what I'm thinking I'm gonna try next is I'm going to try to use the diagnostics ROM, which now is passing the RAM, and it's gonna let us run some of the other tests. So I'm gonna hook up this joystick, and that will let us select ROM test and at least see if the computer is correctly seeing and identifying the ROM and making sure that it can read all the data from it. Okay, so now I select ROM and fire. There we go. Okay, it detects the 464 English ROM, like we said, and the upper basic ROM. So it seems it can read from the ROM perfectly fine. That is very unexpected. So I just spent several days looking into this. I've been checking every connection in the ROM. Everything is fine. I've been checking every connection remotely related to the ROM, and I just can't find anything. I tried also taking the diagnostics ROM that we're currently having the detonator and putting it on the board on an EEPROM. It wouldn't work from there. And I was just going crazy. I was looking at the pull-up resistor in the output enable for the ROM, and everything is fine, everything checks. And I was just starting to go out of my mind, like, what is going on in here? Today, I had a breakthrough. This is one of those things that it's almost embarrassing to talk about this. So when I was running anything from the detonator, I was actually holding the board this way, like this. I was just assuming that it has something to do with the edge connector and the detonator, and I wasn't thinking much about it. I've had to do somewhat similar things like this before, so I just didn't think much about that. But then I realized that with the detonator connected this way, I can actually boot into the system ROM. So let me show you. I need to press the second button, and there you go. We're in basic. So what I'm thinking is that there is something mechanical on the board. that when I do any kind of flexing, it's causing some signal not to work. So actually, I even noticed that. So I'm gonna go there again. And if I push, there you go. Just pushing. And I just pushed anywhere without connection. So there is definitely something that touching it and bending it is making a connection, and laying flat is not working. So that could actually very well be a socket. If there's a socket that is bad, maybe that flex is enough to make connection, and laying flat maybe is not. So I'm gonna have a look at that in the bench. I have a suspicion the problem may come from the gate array, because that problem seemed to happen more when I flexed around this area and the gate array is socketed. The Z80, that's also a potential problem, so I'm gonna check them both. So I think I just see the problem right there. Aren't those single wipe sockets? This is not the first time I've been bitten by that. I hate those sockets. Those kind of sockets only have metal on the inside and not on the outside. I'm willing to bet that that socket was causing the problems. Let's see if the Z80 had the same kind of socket. And I'm kicking myself for not seeing it earlier when I exchanged the gate array. That one also looks single wipe. God, what about the RAM? So I replaced those two myself. So let me just grab one at random. Okay, those are fine. Those are double wipe. So yeah, it won't do any harm to replace those. All right, new sockets are in, and those are perfectly fine, by the way. Those are double wipe ones. Some people prefer the round ones. I think they're called like turn pin ones. I find these to be perfectly adequate for a lot of things and way cheaper than the other ones. The important thing is that they're double wiped, that they have the metal connection on both sides, not like the other ones. And with everything installed in the new sockets, yes. And now I can touch the board and it doesn't go away. Wow, that was a long road to get here. Couple more things and then we're done. First thing, I want to get rid of the crackling noise coming from the speaker. So I'm just going to put some contact cleaner at the volume wheel, and that's usually what it is. It's just dirt that accumulates in there. And then I want to replace the English ROM with a Spanish ROM burned into an EEPROM. And now we should be all set to go. There we go. Everything is working correctly. Let's check the keyboard. Yep, that looks good. And the ñ, right, we have the S, so that's the Spanish ROM. So yes, we got it to work finally. So there you go. It took a lot of effort and a lot of hours, but we got the Amstrad working. It's actually amazing how much harder it becomes to repair something when somebody tried to fix the computer in the first place with good intentions, but obviously making things worse. It's kind of like playing a game. Normally you would play in hard mode, there'll be a regular repair. This is like nightmare mode. It feels like you're fighting the final boss and it's like healing. You fix something and like something else pops up constantly. So I'm glad we got that working. So let's even recap. We had a bad Z80, a bad gate array, 3 bad sockets, and 3 traces that we had to fix. So I'm not surprised that whoever tried to fix that in the first place just wasn't able to, because just replacing one chip and putting another one, they got nothing working. So anyway, that's it for this particular repair. I'm sure we'll have some more repairs down the line. I will see you next time.